Okay, so, man, I'm writing lopsided. It's just like class. Okay, so chapter 21.5, this sort of sums up 21.5, the malonic ester and acetoacetic ester syntheses. These are sort of the same, they're the same synthesis, all right? They work the same way. Malonic acid this is malonic acid. All right, so that's malonic acid. And acetoacetic acid is this. All right, so that's acetic acid, that's an aceto group, so acetoacetic acid synthesis. At the end, I'll come back and explain how these are the same synthesis. Right now, what these are stand-in for is where you need to alkylate a simple single carbonyl enolate with a compound that would do an SN2 or do an E2 kind of reaction. So look at this. What you'd need to do here, you'd have to make the enolate. All right? And again, sorry, O minus. If I want to pull this alpha protein, if I want to make the enolate of acetic acid, I can't make it with an OH here. Right? First equivalent of base will pull the OH off. Second equivalent will pull that off. I'll get this enolate, and then I could do an SN2 reaction that would make that bond. So what I need is 1, 2, 3, 4. I need butyl bromide or something. But E2 is going to dominate. I'm going to get a low yield of desired product. Okay, so go back and watch the earlier videos if you haven't figured that out. These single carbonyl enolates tend to do E2 chemistry because they're strong bases. So the way around that is to alkylate malonic ester derivative. So let's do the malonic ester synthesis. And I'm not going to start with an acid. I'm going to start with diethylmalonate because it costs, nothing. You can buy barrels of this stuff. I don't really know why. Okay, and now the first step, I'm just going to pencil it in here. So a base of some sort. Let's use sodium ethoxide. Ethoxide matches up with the esters. If I use dimethylmalonate, so these were methyl esters, I'd use methoxide. If these were propyls, I'd use propoxide. Match that part with this part. The second step will be my butyl bromide. And then the third step will be aqueous acid under refluxing conditions. And that is going to give me, believe it or not, this desired product. All right, let me take you through how that happens. I'm not going to do mechanisms necessarily, except to sort of explain it. All these mechanisms I've presented elsewhere. So step one is just an acid-base reaction. Okay? And this greatly favors the dicarbonyl enolate. Step one. Step two, then, is an SN2 reaction. All right, so dicarbonyl enolates are weaker bases. They're really good nucleophiles in the SN2 reaction. And so now we get this. All right, so there's 4 carbons there, 4 carbons there. Make sure you keep track of your carbons. And if you're sitting at home, hopefully if you've watched the decarboxylation of beta-diketo acids, you've seen this, and how this is going to work. But now, so this is, I guess I should write this down, keep this. So that's step 2. And now step 3, H3O plus, H2O, 100 degrees, gives you this compound directly. All right, so what happens first? Under aqueous acid conditions, this is chapter 20. We're going to hydrolyze the esters. Again, chapter 20 we've covered. You need to know the mechanism for hydrolysis of esters to acids, either under basic or acidic conditions. Here we're under acidic conditions. And so this will give us, under acidic conditions, the carboxylic acids will be protonated. There's a bad bond. Okay, nothing's going to happen here. We're keeping that enolizable position protonated because we're under acidic conditions. Everything's protonated. And now, you've got 2 carboxylic acids. One of them is going to stick around. If we say this is the acid we want, and this is the alpha position, and that's the beta position. So that is a beta keto acid. And under refluxing conditions, if you go back and look at the last video about decarboxylation of beta keto acids, you're going to lose CO2 out of this. All right, so how long did this video go? That seemed really fast. 7 minutes for the whole Malonic Ester synthesis. So I'm going to take you back through what the desired reaction is to alkylate an enolate. But you can't do that really because it's going to do E2 chemistry. Making an enolate and directly alkylating it's going to be really hard to do. Okay, so then what happens, what we do next, is we use a dicarbonyl compound. And how do you look at this? So the dicarbonyl compound is a synthon. Okay, so basically we're going to be able to hydrolyze the ethyl group, and then we're going to be able to decarboxylate the CO2. So the dicarbonyl compound, and it could be either a malonic ester, so 2 esters, or it could be an acetoacetic ester synthesis, right? And so up here, you're going to be able to hydrolyze and decarboxylate. And so the synthon is that. All right, and it doesn't just have to be those. You can start off with something else here already. You can start off with other stuff here. All right, so the synthon is, this diethyl malonate is a synthon for just ethyl acetate or acetic acid. All right, so we pull this proton off, but what this other group does, what this other ester group does, is it stabilizes that negative charge, that enolate, so that it's a good nucleophile, but it's not a super strong base. And so it won't do E2 chemistry. You can alkylate these really well. Now you have an alkylated diester, but again, right, we can hydrolyze off the ethyl group, and then we can decarboxylate the CO2. And that's going to leave us with that. But under these conditions, you're going to hydrolyze that ester. If you start with the acetoacetic ester, that's going to be a methyl or an organic bid that won't hydrolyze, and you'll be that problem. Of course, if you wanted the ethyl ester here at the end, then you'd have to do a Fischer esterification. And again, if you wanted to get your ethyl ester back, you'd have to esterify it. And that's chapter 20 as well. Okay, so the malonic ester and acetoacetic ester syntheses are stand-ins. They're a way to alkylate an enolate without getting a bad yield. Let me make sure I've got video, because this is actually a really good lesson for life. This is a lesson that you probably know from life, but you know, none of us ever take it into account. This is 3 steps, all right? And you might be saying, this top reaction is 1 step. So, you know, you're human, and so you're thinking, man, I'd rather just do 1 step than do 3 steps. So why don't I just do this 1 step and save myself some work? Even if the yield's bad, surely one low yielding step is better than 3, right? No. So this is going to be like maybe a 15% yield up here, right? This first step, this is essentially 100, all right? If you add sodium methoxide to diethyl malonate, that's about 100. Let's say this goes 90. And then this goes 90. These are both really good reactions. All right, the yield for the 3 steps is 1 times 0.9 times 0.9. So this is going to be overall 81%. It's better to do 3 really good reactions than 1 really crappy reaction, okay? And this holds in almost everything you do. Do it the right way the first time. Anytime you hear somebody say something's a shortcut, what they mean is it doesn't work very well, right? If the shortest way worked really well, it would just be the way we do it. It wouldn't be a shortcut. Shortcuts almost never work. I guarantee you I don't live this in my own life. So I'm telling you this just so you can appreciate when you're doing things wrong. Okay, that's too much philosophy. It's lunchtime.